In this video, we're going to use Oscer's Hckel routine to look at aromatic systems. I want to start by just drawing out a simple triene molecule. So we'll draw out triene, but I'm going to draw it as if it was almost going to form a ring. So I'm going to draw it like this. Okay, let's make that a little bit bigger and center it. Now let's turn on the Hckel routine. So turn on Hckel. Here's auto select. And so this is the highest occupied molecular orbital of hexatriene. And you can see, of course, that there are 6 pi electrons. So this is the third orbital which is being shown. And it happens to have 2 nodes. Why is it 2 nodes? Well, the bottom one is 0 nodes, then 1 node, then 2. So if we click down to, there's number 2, there's the one with 1 node. And then we click down at the bottom, this one has no nodes at all. So the question is what if we turn this molecule into a ring? In other words, we made benzene by connecting the ends. What's going to happen? Well, one of the things that's going to happen is all the atoms are going to become identical because benzene has 6-fold symmetry. So let's draw that bond in. I'm just going to come in and draw this extra bond. Well, sure enough, all the atoms now are the same. This bottom orbital has equal coefficients on all of them. Well, what about the next 2? Well, look at this. Their energies are now identical. Why are they identical? Well, it has to do with this symmetry. We know that the next level has to have 1 node. But now this is a 2-dimensional system in the sense that the electrons are delocalized over a full plane as opposed to just being delocalized linearly in the hexatriene molecule. So both of these orbitals are going to have 1 node, but the node crosses the entire molecule. So here we have a node at an angle like this, and the other one, the next one I know about looking is going to be orthogonal to this one. And so here we go. Here it's orthogonal to this one. Notice that these orbitals are not, they're not perpendicular and to the bottom of the thing. That they're at a kind of an arbitrary angle. But that's because again, there's all parts of this molecule are the same. Is that you can't say that one atom is different than the other. So the way you draw those nodes is completely arbitrary. But the key thing here is that you get this degenerate pair. We use that word degenerate to represent 2 orbitals of the same energy. Now what's the consequence of that? Well, the consequence is that the homo-lumo gap is bigger. These are the highest occupied molecular orbitals. These are the lowest unoccupied molecular orbitals. And the distance between them is a full 2 beta on this energy scale. So let me go back and I'm going to erase that bond we drew in. So I'm going to erase this bond, go back to the hexatriene. Look here. These things are much closer to one another. This here is it. Well, we can look at that exact energy. Down here it says that energy is at 0.45. The top one would be the minus that. So this energy difference is less than a beta. Now, the significance of that is that this molecule is much more reactive than the benzene. Because this pair of electrons is higher in energy, it means that this molecule is a better electron donor. It'll more readily react with acids. It'll more readily give up an electron in a redox reaction. The same way, the LUMO is lower in energy, so it'll be more willing to accept electrons. So this is the key to aromaticity, making the molecule cyclic with a root which makes the whole pi system 2-dimensional, introduces these degeneracies, and the energies between the degeneracies is greater. Now the secret to an aromatic system is having enough electrons to fill a set of 2. So it's going to need 4 electrons to fill this set of 2. And so there's this thing we call the aromatic rule. The Hckel rule is that to have an aromatic system, you have to fill your bottom orbital, which of course requires 2 electrons. Then you have to fill each set of 2 degenerate orbitals, which requires 4 electrons. So it's 4n plus 2. Let's do another example. We'll go over here and I'm going to draw an 8 atom ring. So now let me put in some double bonds. I'm just going to put them in every other position. Okay. And so we'll go to system 2 now, because that's that one. And again, you see we have degeneracy, but our number of electrons is wrong. We have in instead of 8, we have 8 electrons. That's it. The 2 fills the bottom. The next 4. But now we have 2 sitting up here. So this is a diradical. That's really reactive. And it's not a stable molecule at all. What we would want if we're going to have a more stable system is to have we either want this set of orbitals to be completely empty, in which case this is the homolumo gap, or we want it to be filled. So that now the system which is known, but it's still pretty reactive, is actually the dianion. So if I go in here and I just arbitrarily put charge, it doesn't matter which atoms I put it on here. I can go in here and I have to, well, actually, let me turn the Hückel off. I have to redraw the double bond. So I'm going to turn the Hückel off. So I can go in here and I can put a negative charge there. And of course that would I have to redraw my double bonds now. Whoops. So make that a single bond, double bond, single bond. I want to put in a second negative charge. Let me put the second negative charge, let's say, over here. It doesn't matter where I put it. You can put it anywhere. So this is now 8 atoms, but 10 pi electrons. So now if I turn on Hückel in this dianion of 8 electrons, you'll see now the system 2. Now you can see this is filled again. So this again is a Hückel rule because everything is filled. Now this molecule as a dianion is still reactive because those electrons are up high there. But it's much less reactive than it would be if we arbitrarily turn this into a non-cyclic system. So how can I do that? Let me just come up here. I'm going to erase a bond. I'm going to erase this bond over here just for fun. And so now it's the same electrons spread over a linear system. And look at this. Now this pair of electrons way up in the air. There's a very small homolumo gap. So this is much more reactive than the cyclic system. This is the key thing on all these things, is that the cyclic systems simply are more reactive. Now, can we do this with other ring sizes? How about five pi electrons? So here's a 5-membered ring, and this is good. And let me put in a double bond. Oops. Let me turn the Hückel off for a second. Hückel off. Okay. So I'll put in 2 double bonds. Now, in terms of resonance structure, if I want to make that a pi system, delocalized, of course, there's 2 hydrogens there. So what can I do? I can make it an anion. So now we have 6 electrons, 2 from the low pair, 2 from each double bond. This is a 6-electron system. Turn the Hückel back on, and again, we're going to see an aromatic system. This is now system 2. So here we are, and this is a really stable anion. So the cyclopentadienyl anion with 6 electrons is beautiful because, again, the Hückel rule means that this degenerate pair is just occupied, and we have this huge gap now, the homolumo gap. And again, if we do our same trick, let's just arbitrarily go down there and erase the bottom bond. This will become a band of orbitals again, and the homolumo gap again now is much smaller. So the key thing about the cyclic systems is that it makes the degeneracies. And when you have a set of degenerate orbitals exactly filled, it's 4 electrons in it. You don't want 3, you don't want 2, you don't want 1, you want 4 electrons. So that's the 4n plus 2 rule. That's where you get an aromatic molecule. Now, by far, the most important aromatic systems are the ones of 6 electrons. I would say, 99% of the molecules that we talk about as being aromatic are based, single rings are based upon the 6 electrons. Where the 10 electron systems with those things come in, you should make molecules bigger, but they're just rare and less common, but they're still fun to look at. So anyway, that's a nice introduction. I hope it's a nice introduction to what causes aromaticity. Thank you.